Wait, one more person is logging in. Good afternoon, everybody. Welcome to another wonderful afternoon of Chem 170 with your host, me, Dr. White. Have you noticed my eyes go when I point to them? I don't know how that happened. But anyways, it's being obnoxious Wednesday. All right, important things. First of all, you should have received an email with the password for test number 1. You go to Blackboard, wrong school, D2L, and you can download the PDF file for test number 1. You have until tomorrow, 4 p.m. to get your answers uploaded for test number 1. Now, if you don't have a printer, that's okay. By the way, I think this is over a year and a half old. HP sells nice black and white printer scanners. I think that cost me $200 from Staples, which is pretty cheap compared to years and years ago. And HP was usually about $1,500. Anyways, I'm being sidetracked. You can write on a piece of paper the problem number, like if it's 1A, and your answer. You do not have to write the whole problem if you don't have a printer. Now, if you have a scanner, scan it, upload it as a single PDF file. If you don't have a scanner, but I think all of you have access to cell phones with cameras, take the pictures of each page, and then there's different ways of how to convert that into PDF file. I have instructions how to do that also. Let's go to D2L. And if we go on the assignment area, you'll see test number 1. This is the file you download, and you have the password. If you didn't receive the password, email me. And here are instructions, like I said, how to convert that. And here's instructions I found out from another faculty number of years ago that there are students who wanted to use the app Cam Scammer. Do not use the paid version with all the bells and whistles. Use the free version. That's all you have to. And there's another way of doing that. And I have that described in these instructions. And if we move this like this, and I go like that, notice the deadline is, or due date is tomorrow, 4 p.m. So you have plenty of time. How much time should you take on the test? Whatever you need. When we're face-to-face on test 1, most students are done within about 35, 40 minutes. I give them 50 minutes and everybody's done by then. Unless you haven't studied, well, then you could have all day and it wouldn't help. So remember, look at your email, student email. You'll see the password email. Use that to open this file to take test number 1. Let me log out of D2L because I don't need to go there anymore. All right, another important thing. Remember hand-in labs. And today, lab we did last week is due today. Make sure you hand in your labs. I uploaded the last lab you handed in. If you don't see a score there, that means I had trouble reading your lab. And one of you, I did have trouble. There was nothing there for me to open. So resubmit it or email me, and I'll have time tomorrow to email that person. All right, another thing I forgot to mention about the labs. Hold on. Oh, I just rebooted. Test number 1, I will have posted in D2L by Sunday, 1 p.m., your total test score. And by Sunday, 1 p.m., each of you will get an individual email with the points you got for each answer on test number 1. On Monday, next Monday, I will go through all the answers for test number 1. I like my special effects. But anyways, I will go through that. However, I will cut it out of the video, the part where I go over the answers for test number 1. But if you can't make it to class, which is a net course, so you don't have to, I will help you out and go through any of the questions you want me to on test 1 during my office hours. So by Sunday, 1 p.m., and when I do put them in D2L, I'll send out an announcement, post it, and send out an email that your grades are available. All right, let's see. I think that's everything for now. Oh, if you have any questions while taking test number 1, today after 4 p.m., from 4 to 9, about every 2 hours, I'll check my email. Also today, I have my office hour from 5 to 6:15. If you have any questions, stop by or email. And as I've always said, there's no such thing as a dumb question. And you might have a question during one of the things I wrote on the test. All right, I think we covered everything. So it's time to get back to work and talk about alcohols. By the way, did anybody drive by a gas station and think of alkanes? Did anybody look at the barbecue they were using and the white tank has propane? That's an alkane. I like that serious look. Oh, come on. Anybody happen to look at baby oil, Vaseline, or a candle and think of alkanes? Ah, come on, give me a break. Remember, it won't hurt for you to think about organic chemistry when you're not in my lecture, because organic chemistry is all around you. I stole that from SpongeBob, and it won't hurt you to think about that. All right, let's get back to alcohols. Let's find out where I should be in alcohols. All right, yes, yesterday, Monday, hold on, my eye itches. There we go. We talked about oxidation of a primary alcohol. Primary alcohol is when you have one R group on the carbon with the hydroxy group, that's an alcohol, and the O bracket O, close bracket, is the shorthand for any oxidation reagent. And there are a number of them, but my gift to you this semester, I'm not going to make you memorize all those, like potassium permanganate, sodium dichromate, potassium dichromate, manganese dioxide, and so on. And the general reaction, take a primary alcohol, and I'll never ask on test or final what's the type of alcohol, but you need to realize what you're dealing with. And you lose a hydrogen here, hydrogen there, and you form a carbon oxygen double bond, which you'll learn in 2 chapters is an aldehyde. And we went through some examples, but as I've already mentioned, on test 2, I will have not one synthesis, but 3 or 4 syntheses. You've already lost your rookie status by then. So let's have some fun. What would I oxidize to make that molecule? Your turn. And for those of you who have showed up, thank you. And for those of you watching me on YouTube, taking this class, thank you also. Also, any of you who showed up, turn on your webcam. That makes Dr. White very happy. I see one of you have. Thank you. And when you're done, give me a thumbs up. a thumb side. I know your wrist doesn't work today. All right, I think everybody's done. Let's take a look at this. What's different here? Oh, I forgot to mention, bad Dr. White. Remember, for test number 1, it's true for 2, 3, 4, and the final. How many bonds to carbon? 4. Ooh, it's broken. I got to get that fixed. How many bonds to carbon? 4. Remember, 4 bonds to carbon. Also, do you break carbon-carbon single bonds except for combustion? No, that's going to be your 2 biggest friends. And also, when you look at a molecule, look for what's different. What's not carbon, what's not hydrogen, should get your, or a carbon-carbon single bond should get your attention like this. Did I get your attention? Hopefully it did. I love these. They're made from by a German company that unfortunately went out of business. I've got 4 of them. They never leave my house because you can't get quality whistles like that anymore. But anyways, back to chemistry. So if we look at this molecule, what's different? Oxygen. It's double bonded to carbon, hydrogen, and on this carbon, there's carbons. This I'll call R. And what do you oxidize? That's what this symbol means to make this molecule. And that is a primary alcohol. The carbon double bond to oxygen will be the carbon with this COH group on it. Now, since we don't break carbon-carbon single bonds, and if you notice we're not adding any carbons, we will later on, but not this reaction, I end up with 3 carbons. I better start with 3 carbons. The carbon with the carbon double bond to oxygen will have an alcohol. And here's my R group, 2 carbons. And I know there's 4 bonds to carbon, so I can put in my hydrogens, and I'm done. And that's how you oxidize an alcohol to a aldehyde. All right, let's move on. Now you can oxidize primary alcohols. Guess what? You can oxidize secondary alcohols. And this is secondary alcohol. You oxidize it, you lose a hydrogen here, hydrogen there, form a carbon-carbon double carbon oxygen double bond. By the way, my software likes to do this. Every bend in the line is a carbon, so there'd be a carbon here, carbon there. I forget to do it, and that's shorthand. Organic chemists are lazy, and I forget to do that. Let's look at this reaction on my whiteboard. Remember, this means oxidize with an oxidation reagent like potassium permanganate or sodium dichromate. By the way, I did oxidations when I was doing my PhD thesis to make certain molecules I needed. And what's attached to the carbon here, R and R prime, are still there because you don't break carbon-carbon single bonds. And you lose this hydrogen, and you form a carbon-oxygen double bond. And you'll learn later in 2 chapters, this is called a ketone. By the way, I should have mentioned, this is called an aldehyde. And you'll learn about that in 2 chapters. And you'll also learn that Dr. White loves aldehydes and ketones. I'll talk more about it when we get into that chapter, but I really do. They've been good to me. I've been good to them. All right, let's take a look at this. Now, one thing I'll be doing interchangeably, I can write this alcohol this way and an equivalent way, identical in the sense of same molecule, I can write it this way. And they're both the same secondary alcohol. Remember, 2-degree sign ROH, secondary alcohol. And if I oxidize it, what product do I get? Well, if I lose this hydrogen and this hydrogen, I'll call one of these R and one of these R prime. Remember, R means something with carbons. R and R prime is like in math, X and Y. They're numbers. Well, here there's carbons. Our general reaction right here says I lose this hydrogen, this one, and I'll get this molecule. The R groups are still attached to the carbon right here. Now, if I use this way, it's the same molecule, but a different way of writing it. You same thing, you lose this and this, and you form a carbon-oxygen double bond, and what was attached to it, R prime and R, doesn't matter what you call, are still there. Both are still the same molecule, different ways of drawing it. I better let you have some fun. And now it's time for you to have some fun. Why scratch my back? Don't look. And when you're done, give me a thumbs up or a thumbs down or any other emoji. Did I tell you I've been trying to get people to change and not call them emojis, but call them symbolis because they're symbolic or symbols? It hasn't gone far. As you can tell, not everybody's saying nobody's saying except me, use a symboli. Thank you, Christiana. Thank you, Andrew. Oh, a happy face. See, I told you organic chemistry is fun. And it is. But then I'm biased. Everybody's done, so I can get to work. So how do you proceed? You look at this molecule and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon? Ooh, oxygen with a hydrogen and a carbon, and carbons on that carbon, R and R prime. It's a secondary alcohol. If I oxidize a secondary alcohol, I lose this hydrogen, and the carbon with the hydroxyl group becomes carbon double bond to oxygen. What was attached to that, R and R prime, are still there. And in this case, what's R? Doesn't matter what you call R and R prime. R is one carbon methyl group. R prime, 3 carbons and propyl. Guess what? They'll still be on this carbon, methyl. And propyl. Why? Because do you break carbon-carbon single bonds? No, and you don't. Did I tell you the story? Before I started doing that first semester, students I ever taught organic at ECC, students were doing all sorts of weird things. And I started doing that and they stopped and they got better grades. All right, now the carbon with the hydroxyl group will now be double bonded to oxygen. And we've made a ketone. And Dr. White's happy because I love ketones. All right, now something you couldn't do in an aldehyde, or I should say in a primary alcohol, but you can do in a secondary, you can have the following reaction. Let's do a better ring. Let's get the eraser. Hopefully I'm not having a bad ring drawing day. That's better. And the question would be, give the organic product or the products for the following reaction 3 points each. Remember, each of these reactions allow us to make molecules that are used in our daily life. And later in the semester, you'll see some of these are used to help make perfumes, other molecules, things like your fabric softener, your laundry detergent. They're all made using the general reactions I'm teaching you. I don't know if I mentioned this, excuse me, and we'll talk a lot more later in the semester about it, but 2 areas that use very, very sophisticated, actually 3 areas. Any personal care items is some really high level organic chemistry. Nail polish is very high level organic chemistry, and cosmetics and perfumes are very high level organic chemistry. Well, let's get back to this. We look at this molecule, what's different? Ooh, an oxygen with a hydrogen on this carbon. And what's this carbon? It's got a hydrogen, you don't see it. It's got carbons here and here. But in a ring, R and R prime are connected together with other carbons. So this is a secondary alcohol. Again, this carbon is this carbon right here. Over here, I have the beginning of R prime. Over here, the beginning of R, and they're bonded together through other carbons. In this case, this molecule is a secondary alcohol. And if we oxidize it, you know what you'll get. You lose 2 hydrogens, and you form a carbon-oxygen double bond. Now, do you break carbon-carbon single bonds? No. So if I start with a ring, I better end up with a ring. The carbon with the hydroxyl group, which is this carbon, will now be double bonded to the oxygen. And we have a ring. Remember, every bend in a line is a carbon, and right here, there's a carbon, because that's part of the ring. And that's secondary alcohols making ketones in a ring, which Dr. White did his PhD thesis on, very specialized ketones. Your turn. Give the organic product or products for the following reaction. 3 points each. Oh, after test number 1, you'll understand why I say that. And you'll also learn why I call the practice problems. Hint. And you know what you should do when you're done. Give me the done signal. Thank you, Christiana. Thank you, Andrew. And thank you, Ignacio. All right, let's look at how do you do this. Look for what's different, what's not carbon, what's not, oh, an oxygen with a hydrogen. And don't forget this bend in a ring is a carbon. I've got carbons here and here. So this is a secondary alcohol. If you oxidize it, you'll lose the hydrogen here and hydrogen there. And what's attached to this carbon, R and R prime, since you don't break carbon-carbon single bonds, come along for the ride. And they do. I like that. And they do. I started doing that about 2 years ago. I don't know why, but I do. All right. And you'll lose those, and you'll form a carbon-oxygen double bond called a ketone, which I'll teach you in 2 chapters. Now, do you break carbon-carbon single bonds? No. So I have this ring and methyl group, which are my R prime and R attached to this carbon, are still there. And the methyl group here on the ring is still there. And what happens? This becomes a carbon-oxygen double bond. And that's your product. And that's how you do it. Oh, let's have some fun with this. What molecule would you react oxidize? That's what bracket O, closed bracket, means, using reagents like sodium dichromate to make that molecule. And this is the best and fun part of organic chemistry, synthesis. But I'm biased because I'm a synthetic organic chemist. Remember, synthesis means to make. So how would you make that molecule? Thank you, Christiana. And for you, all of you, thank you, Andrew. And for everybody out in either here in class or out in YouTube land, if you're taking this for like the second time, which the other students in the past have, hopefully this is going better this time. If it's not, always feel free to come to my office hour if you need extra help. If you can't make it to my office hour because you're working, let me know. If you really, really need extra help, I'll find a way to help you out because I'm on Zoom now and I can set up a Zoom meeting whenever I want. So, is everybody done? I think so. So, how do we find out? What do we make? We look at this molecule, what's different, what's not carbon, what's not, ooh, an oxygen, double bond to that carbon with carbons attached to it on both sides. And this is a ketone. And how do you make a ketone? You oxidize a secondary alcohol. Now, what was attached to this carbon double bond to oxygen is still attached, which is this carbon right here. Do you break carbon-carbon single bonds? And I'm not adding any carbons here. So if I end up with a ring with a T-butyl group, I better begin with a ring with a T-butyl group. And I do. And the carbon that's double bond to oxygen in the starting material has a hydroxyl group, OH. I can do that, and I'm done. If I take this molecule and oxidize it, this right here becomes this, which is this. And that's how you do it. Now, it's time for Dr. White to bring back some old memories. So please forgive me if I'm going to be smiling too much. But one molecule I had to make for my PhD thesis to prove a certain theory and my PhD advisor were working on was, and this is a very complex ring system. It's called a 2,2,2 bicyclooctane ring system. And my research, good memories coming back now, I had to oxidize this. Which I did. Whoops. To make this aldehyde, and I did. It helped prove the theory we were proposing, and it was correct. It wasn't a theory, it was a fact. Oh, old memories are good. That was a long time ago in a galaxy far, far away. All right, let's get back to work. Now, note, tertiary alcohols cannot be oxidized. What does that mean? Well, if you have a tertiary alcohol, that means 3 R groups on the hydrocarbon with the alcohol, and you try and oxidize it, the answer is no reaction. It just doesn't. Why? Because if this became a double bond to oxygen right here, there'd be 5 bonds to that carbon. That's not going to happen. It won't. Trust me. I'll bet any amount of money. If I tell you I bet, that means I already know I won. So don't ever bet with me. I don't bet with students, but if you ever had a thought about it and I say, let's bet, don't, because I know I've won. Now, let me tell you something personal about Dr. White. First of all, I teach by my golden rule of teaching. I don't do to my students what I didn't like done to me when I was a student. And when I took organic chemistry and you were asked on a test, here's a series of reactions, give the product or products, and one of the answers was no reaction, that's wrong. You asked me to put down what's the product, there better be a product. And therefore, this I will never, ever put on a test or a final on any of my tests, on my final. If you put down the answer, no reaction, it will always be wrong. Because if I ask you, give the product or products to something, something's going to happen. All right. Now, when you have alcohols, you can have molecules, alcohols, with more than one hydroxyl group on it. And I'm going to turn the switch click off, but this is good for common understanding. One are glycols, ethylene glycol. This is a common name. But you should be able to recognize that this is an alcohol, a molecule with 2 alcohols. Now, ethylene glycol, when you mix with water, we call that product something. It's called antifreeze. And remember I talked about for the first lab, the colligative effect? When you mix 2 solids together, the melting point goes down and the boiling point goes up. Well, that happens with liquids. Why this is a good antifreeze? Because when you mix, excuse me, ethylene glycol and water, the melting point goes way down. If you just have water in your radiator and the temperature outside gets below 32 degrees F, your radiator is going to freeze and your car is going to be damaged. And because of the ethylene glycol and water mixture, it doesn't happen. That reminds me, I remember one time many years ago, it was New Year's Eve. I was coming back from somewhere. Don't ask me why I was out at this time with this weather. But the night temperature, I remember I was driving around at 1 in the morning coming home, and the temperature, not the wind chill, was minus 22. It was really cold. But I had ethylene antifreeze, so my radiator didn't freeze up. And the same thing, the boiling point goes higher. So in the summer, the water, if you just had water in your radiator, would start boiling. With ethylene glycol water mixture, it's a lot higher. Now, there's another molecule called glycerin, also called glycerol, but glycerin, and that's, oh, by the way, I should point out, ethylene glycol is highly poisonous. That's why antifreeze is colored the way it is, so you know not to drink it and think it's water, because you'll die. Now, this is glycerin, and that's a molecule with 3 hydroxyl groups, and glycerin is safe. How do I know this? I'll teach you later in the the semester. That was last semester was summer. Later this fall, that your body breaks down fats and oils and makes one of the products in your body, glycerin. Now, next thing, and we'll talk more about this when we get into carbohydrates, sucrose, table sugar, it also is a molecule with more than one alcohol. Now, just because something's an alcohol doesn't mean if you consume enough of it, you'll get inebriated. And if you notice, here's the structure for sucrose, table sugar, and there's 1, 2, 3, 4, 5, 6, 7, 8 alcohols in there. Trust me, if you consume a couple tablespoons or more of sugar, you are not going to get inebriated. You may get an upset stomach, but you won't get inebriated. All right. Now, the last I'd like to talk about is called polyvinyl alcohol, also abbreviated PVA. Now, this is called a polymer. And think of a polymer as like a long train with a lot of boxcars connect together. And we show that by a bracket. And this is repeated over and over again in polyvinyl alcohol. Notice hydroxy group on a carbon alcohol, where N here is on the order of, are you ready for this? 1,750,000 to a million. That's huge. Now, all of you probably have polyvinyl alcohol in your house. You say, no, I don't. Yes, you do. Well, how do I know that? Well, if you mix polyvinyl alcohol and water together, you have this white gooey stuff you call Elmer's glue or white glue. And that's polyvinyl alcohol and water. Now, I worked for a company before I worked for them, they sold off this division, but I used to work for Borden Chemical. And Borden made a lot of glue. And the original glue was from another molecule that came from milk, which is why Borden got into it. And then they switched to polyvinyl alcohol. All right. Now, I'm turning the switch totally off quick. Let's talk about antioxidants. Phenols, molecules with a benzene ring and a hydroxyl group, are antioxidants. Now, air, which has oxygen, can react with organic molecules that change them to things you don't want happening. And this happens with food and things like lubricating oils. And this causes what's called radicals. And radicals, when they are formed, are very reactive intermediates. I could do a whole semester course on the chemistry of organic radicals. It's that interesting of an area. I'm obviously not going to. And they break down the food and lubricating oils. Now, there's certain molecules that react with radicals to form stable intermediates, essentially stop the oxidation or the reaction of the radicals. And it's also called oxidants. Radicals are oxidants, but not the oxidation I just showed you. And these form stable ones. And two of the more famous ones are BHA and BHT. And BHT is shorthand for butylated hydroxytoluene and has this structure. Now, each one of these on the side, oh, by the way, thumbs up, people. You see that structure on your, thank you. This is a T-butyl group. This is a T-butyl group. This is a methyl group, benzene ring, hydroxyl group. This is a phenolic compound. And this, when it reacts with a radical, sort of ties it up, neutralizes it, sort of. And this used to be in potato chips with another one, which is one of the reasons Dr. White loves T-butyl group. And that was antioxidants. And other foods have antioxidants, and they help stop the oxidation. Now, in potato chips, they don't put this in there anymore because a number of years ago, some organic chemists found a way of making the bag material out of a special way that inhibits oxygen from getting into the potato chip. And because of that, when they make potato chips and bag them, they use that material. That's now all potato chips use that material for their bags. They put the potato chips in there, then they blow in nitrogen gas to get the oxygen out. And that's the other way, and it's cheaper than using an antioxidant. Now, again, switches off, but a couple of years ago, and I have no idea if this is true or not, some scientists were theorizing that radicals formed in your body cause aging. Is that true or not? I have no idea. I haven't heard of it too much of that, but that's why people theorize consuming enough antioxidants in your diet helps you stay healthy. Is that the reason why it ties up the radicals? I don't know. Things like spinach and other green leafy vegetables have a lot of radical phenolic antioxidants in them, and just thought I'd let you know. By the way, I used to tell my mother when I was in college and grad school, Mom, I should eat more potato chips because the antioxidants keep us healthy. She didn't buy that at all, not at all. I tried. All right, let's move on to a new functional group in this chapter, and that's called thiols. And I have to warn you, this part of this lecture is going to stink, and I mean really stink. So be careful. Now, what's a thiol? It's a sulfur analog of alcohols, and a thiol is, instead of an oxygen on a carbon with a hydrogen, it's a sulfur, and this is a thiol. Now, I'm not gonna ask you to learn the IUPAC nomenclature, but it's like alcohols, but you drop the E, instead of using OL like an alcohol, use THIOL, thiol, for the ending, and they stink. Now, you're going to hear me this chapter sometimes I'll say mercaptan. Until about 1980, 85, I might be off by a couple of years, the IUPAC name was mercaptan, and they changed it around then to thiol, which is good, but I learned it under mercaptan, and I still think of that. Now, the important thing you should know, thiols stink. What do you mean thiols stink? Well, if you smell a thiol, you're going to say, oh, does that stink? How stinky could that get? I'm going to skip a slide and go to this slide. Everybody see skunk odor on your slide? Have you ever been around where a skunk let loose or an animal got skunked? I've never known a person who got skunked. Well, I'm lucky. That stinks. If you ever drive by an area where a skunk let loose, it stinks. And someone analyzed the defensive weapon of a skunk, what they let loose at, the liquid they spray. And it contains 45% of this thiol, knows carbon, SH, has 25% of this, and the remainder is water. And you know how stinky that can get, real stinky. Now, onions and garlic, which Dr. White loves onions, I love garlic, they stink too because of thiols, but that's a nice stinky, but some people don't like it. But Dr. White loves onions and garlic. Now, I'm turning the switch on, click. I have to tell you about a very sad tragedy. Back about, and the switch is on, so pay attention. Back about 1935, in this high school in Texas, or school, I think it was a combined school, that was pretty new, had been just built. There was a horrific explosion and fire. Over 130 students and teachers were killed like that. Many, many more were severely burned. And when they investigated, it was that there was a leak in throughout the whole building of natural gas, methane, CH4. And it was due to leaky pipes. And what you don't know, but I do, you can't see it, it's hidden right there, a light switch, regular house light switch. When you turn on or off, inside there's a spark. And if there's anything flammable about it, boom. And the theory was, one theory was someone turned on a light or something in that whole building, sparked, and there was enough methane in there, and it blew up and caused a fire. Another sort of legend was they were having a chili social to make some money for the school. And who's ever in the kitchen near the gym where they were cooking the chili left, and the flames went out and the methane filled the whole place. Somebody lit a cigarette. Back then they did smoke in high schools, adults did, or turned on a light or anything, and it blew the place up again. Either way, the tragedy happened. And you're going to say, Dr. White, I can smell a gas leak. And the answer is you can't. Why can you smell a gas leak? Because of that tragedy. After that tragedy, the Texas state government empowered a commission to find a way to make natural gas safe, because methane is odorless. You can't smell it. Well, they found a thiol that stinks, and they put that thiol in the natural gas, and now you can smell it. And what is that thiol? T-butyl. And again, switch is on. And this is the common name, not the IUPAC name. And this stinks. How bad does it stink? How many of you have ever smelled a gas leak? You can smell it pretty quick. Oh, well, this compound is so stinky. To smell that gas leak, they put somewhere about 1 to 4 pounds of T-butyl thiol for every billion pounds of methane. That's 4 parts per billion. That's how stinky it is. Now, do I have time? I'm going to go a couple minutes over into our first break. So I want to tell you, let's take a break and we'll come back. Come back at 1:56 and you'll get a great Dr. White story. At least I think it's great. Let's take a 5-minute break. Don't forget, you should have gotten the email with the password for test number 1, and I'll see you in 5 minutes. I can go stretch. Time to get going. Welcome back. Well, let me tell you a story. Now, when I was in grad school, I went to Michigan State, and when I started the building, the chemistry department building in Michigan State was only a couple years old, 2 or 3 years old. Beautiful building, probably the finest chemistry facility I've ever been in. And it was big. We're talking 2 city blocks long, 5 stories, and then it had a basement and a sub-basement 2 blocks long. Huge building. There are a lot of people in there too. I think when I was there are like 45, 50 professors, maybe 35, and about 400 grad students, plus all the students who were taking labs, the undergrads who would come in. So it was huge. We had fire drills once a month because it was a chemistry building. And in November, late November, I remember this, we had the fire alarm went out. And in a chemistry building, you don't just stick around, you get out. And luckily I was in the lab, my lab I was working in with the other grad students. And I put on my jacket because it was cold out. It was near Thanksgiving and it was a slight mist or snow. And we went out there. And what you don't know is in the chemistry department, there are 4 branches of chemistry: organic, inorganic, analytical, and physical. And when you have something like that, all the organic students were in a group together, the physical were another group, and organic. So we're standing around and we're talking. And usually after about 10 minutes or less, everybody's been out. The announcement is safe to come back. Drill is over. Well, 10 minutes, 15 minutes, 20. And it's not. And a fireman happened to walk by our group, and I or someone else asked, "What's happening?" And the fireman said, "Gas leak." And one of us, and I don't think it was me, but it could have been, all right, what idiot dumped T-butyl mercaptan, T-butyl thiol, down the drain? It turned out it was an inorganic student who was an idiot. And what happened was, dumped it down the drain instead of properly disposing of it. There's a way to get rid of the odor. And he didn't. And it went down the drain. And in the basement or sub-basement, there was a water trap for a drain down there that had dried out. Well, the vapors came right out. A janitor smelled that gas leak, and he did what he should have done, which I was glad he did. Called the fire department and said, "There's a gas leak in here." And that's the story. But you should remember that you can smell natural gas, methane, because there's T-butyl thiol that's added to it. Now, if you have propane, because of the difference in solubilities, they use a different thiol, but there's a thiol in there. I found out about that about 2 years ago, I think it was. I didn't realize it because I've never worked with propane. But there was a student I had who did, and said they put a different one in there, but it smells stinky too. And with that, we're done with this chapter. It's time for a new chapter. Oh, I forgot to do a new chapter. I'll wait until everybody's done drinking. New chapter time. And that new chapter deals with ethers and epoxides. And I should warn you, I have worked with epoxides in the chemical industry. And I also have a great story about ethers. Now, what is an ether? An ether is where you have an oxygen bonded to 2 R groups. This is an ether. And hold on, I see a question. And the answer is yes. Epoxy group, epoxide, yes. Who asked that? Ignacio did. So the answer is yes, it is. See all the neat stuff you're learning in my class? We haven't even gotten to the good stuff yet. Wait till we get to the good stuff. You'll be amazed. Anyways, this is an ether. And ether is a functional group that has its own chemistry. Now, nomenclature. Good news, I'm not going to teach you the IUPAC nomenclature because most organic chemists only use common names. And how do you do common names for ether? You name each R group on the ether as if it were an alkyl group, and then add the word ether to the end. So, and most ethers that are in use today are small molecules. Does that look like a small molecule? It's a big molecule. All right. See, bored. I better get to work. So let's look at the following molecule. And the question is, what functional group, what type of molecule do you see? Well, you look for what's different. What's not carbon, what's not, ooh, an oxygen. And notice I have carbons here and here. R, O, R prime. That makes it an ether. And how would you name that? Well, what's this CH3 group called? Methyl. And this is the common name. What's CH2, CH3? Ethyl. And because it's an ether at the end, you put the word ether. And so that'd be methyl ethyl ether. Since it's a common name, there's no rules which go first. You could also call it ethyl methyl ether. But this is an ether. Oxygen with two R groups on it. And R and R prime means they could be the same or different. And here's one for you. What would be the common name of that molecule? And when you're done, give me a thumbs up. You know the drill. Well, in case you forgot it, I just told you it. Thank you. Everybody, thank you. What is ether work is thirsty work. So how would you name the common name? Well, what functional group is this? What's different? What's not carbon? What's not hydrogen? Ooh, oxygen. With carbons here, carbons here. One of these I can call R prime, like X and Y, because they're different. And this is an ether. And here we have a methyl group. And what's this right here? Isopropyl group. 3 carbons, the center carbon is isopropyl. And it's an ether. And you could have also written isopropyl methyl ether. And that's the common name. Now, does Dr. White know the IUPAC rules for this? Yes. But do we use it? No, but let me show you why we don't use it. Switches off, click. For your IUPAC, you name the smaller of the alkyl group as what's called an alkoxy group. RO is called an alkoxy group. Name the larger group per alkane nomenclature and name and number the alkoxy group as a substituent on the larger alkyl group of the ether. See, for example, this is why we use common and not IUPAC. Let's look at this molecule. And again, switches off now. Now, this is an ether. Why? Oxygen, carbons, carbons. Now, the common name would be methyl N-butyl ether. The IUPAC name, the longest chain is 4, so it's butane. This, and you don't have to know this for my class, but I'm just showing you, that's called the methoxy group, alkoxy. And this is carbon 1, so that's 1-methoxybutane. Which is easier name to get to? The common name, which is why organic chemists use that, unless you absolutely have to use IUPAC, which is very rare. Oh, let's do one more common name. Let's have some fun. Let's see if you're up to it. And here we go. What's the common name for that molecule? Thank you, Ignacio. Am I pronouncing that correctly? Thank you, Christiana. Am I pronouncing that correctly? And thank you, Andrew. I better not let anybody out.
Yes.
You left out. Am I pronouncing Andrew correctly? Am I correct pronouncing Dr. White? Oh, it's being obnoxious Wednesday. All right. How do you name this? What's different? Oxygen. We have carbons on both sides. It's an ether. And the common name each group. Well, this is an ethyl group. This is an ethyl group. How do we say to an organic? Diethyl ether. Because they're two ethyl groups, diethyl. You wouldn't say ethyl ether. You'd say diethyl ether. Now, it turns out diethyl ether is probably the most widely used ether of all the ethers in organic chemistry. When I was in grad school, sometimes I'd go through a gallon a day using this for various things. I use a lot. Now, it's so popular that a lot of people just call it ether. Have you ever been around people who do automotive work and they put ether in the carburetor to help start the car? Don't, because it's dangerous. They say, oh, let's put some ether in there, or they spray it in, and that's really diethyl ether. Now, let's talk about, and switches off, ethers, the smaller ones, are very low boiling liquids. Diethyl ether, the heat from your hand will cause it to boil. That's how low. If you have a beaker of ether and you put your hand around it and hold it for a while, it will start boiling. The other thing, ethers are flammable. They make gasoline look like something that's not flammable. That's how much more flammable they are than gasoline. And unlike gasoline, ether has a higher density than air. So instead of floating off, if you have ether vapors, they stay right where they are. And if you've ever seen an ether fire, and I have, it just shoots right across where all the vapor is. And it's quite dangerous. Now, I don't have a slide for this, so I better go. Now, one of the things that I've been doing more and more, why are we learning about this? And the obvious answer is you want to get a good grade in this class because someone told you you had to take it to get in a program or a school. Well, why learn about ethers? Well, it turns out back in about 1830, 1835, medical science found out that diethyl ether, if you inhaled it, it knocked you out. Good. And there were no after effects instead of you like, and diethyl ether was the first inhalation anesthetic. Before you have an operation, they put you out. Well, back then, they didn't have stuff like that. And that was the first one. And it was heavily used in the American Civil War in the 1860 to 1864. Now, the bad thing about diethyl ether, it's flammable. And up through the early 1900s, if there was a lamp around with a flame, and enough vapor got there, you had a fire. And later on, if you were cauterizing a blood vessel with electrical spark, heat, and there was vapors coming out of the patient's mouth from the ether in their lungs, you had a fire. You probably killed your patient, and the surgeon hands were badly burned, and you might have lost the surgeon because his hands were now badly burnt. Well, it turned out medical science or organic chemists found out that if you replace some of the hydrogens with halogens, then it's not flammable, but it still knocks people out. And let's see if I can find it real quick. Got it. Everybody see that structure on your? Thank you. This has two carbons. This end carbon has three fluorines. This carbon has a chlorine, a hydrogen. This has a carbon with two fluorines and a hydrogen. And this has the trade name isoflurane. Now, time for another doctor. Wow, you're getting a lot of stories tonight. When I moved into this house a long time ago, I did something stupid. I was moving boxes of books that weighed like 120, 150 pounds up and down steps. And what was the stupid thing I did? I didn't put on a weight belt. Well, guess what? It popped my hernias. Ouch, ouch. And I found a good surgeon. I went to my doctor and said, well, you have hernias. Got to find a surgeon. And a friend of mine, of my brother-in-law's, had just had heart surgery by this really great surgeon. So I went to him and he said, yep, I got to operate on you. You got double hernia. Well, I had heard good things about him and I checked up other things and I scheduled it at this hospital. Back then it was he worked out of Evanston. And I had a 1 o'clock, that's when it was supposed to start. You know how you get there an hour early, they get you in your gown all ready to be wheeled in on a gurney. And so about 10 minutes before, I got wheeled in or wheeled to the outside of the operating room 5 minutes before. And then I'm just laying on the gurney. They have a blanket over it and you have your operating gown on. And I'm waiting. I see a big clock. It's 1 o'clock. I'm waiting. It's 5 after 1. I'm still waiting. And one of the doctors came over to me, and he was the anesthesiologist, and said, I see you're looking nervous. You don't know about your surgeon. What do I know about my surgeon? He's never on time. He's always late. So just relax. And he says, what do you do? I said, I'm a synthetic organic chemist. And I asked, what do you do? Well, I'm your anesthesiologist. And he comes over with a bottle and says, this is one of the things I'll use. It was isoflurane. And I looked at the label, saw the name, what the molecule was in there. I said, this has this 2 carbons here with this. And he said, I got to get to work. I said, what do you mean? Well, can't you tell your surgeon's here? No, he had a mask on and his hat on. I couldn't tell at first. And By the way, it was quite severe operation. I really messed myself up. I was on the operating table for a double hernia over 4 hours, and that's long. And afterward, he said, boy, I really have to construct it, but you won't have to worry. And that was many decades ago. Well, yeah, more than 20 years ago. And I haven't had that problem. But if I lift heavy things, I put on a weight belt now. But guess what? I survived. In case you were wondering, did he live through it or not? But what they put me out, one of the things was an ether. Now, how do you make ethers? There's one main way. By the way, click switch is on full blast. That's called the Williamson ether synthesis. Dr. Williamson discovered it or created it. And that's where you take, this is called an alkoxide. Which I really am not talking about other than here. Alkyl halide, R group with a halogen. And X here can be chlorine, bromine, or iodine. And this attacks the carbon with the halogen, kicks it out. You have sodium plus, X minus, you get a salt. But you know, I only asked for the organic products, and you make an ether. And let's take a look at this. And let me rewrite it again. I keep on writing cursive, or I should print it. All right, so if you have an alkoxide, this attacks. By the way, did I tell you organic chemists are violent? We use terms like attack. And if I were with colleagues, I'd use the same terminology. The carbon in R prime that has the halogen, this oxygen is now bonded to the carbon in R prime with that had the halogen. If I were to ask, give the organic product or products for the following reaction, just the organic, what would you give? Well, you look for what's, oh, no, we get to look at two organic molecules for what's different. We'll do more of that the rest of the semester. Well, I've got an oxygen with a minus charge, sodium cation, carbons. This is called an alkoxide. And later on, I'll show you how to make them, but I won't include it in the lecture part of this class. This compound, carbon, carbon, ooh, halogen on a carbon, alkyl halide. Remember, X can be chlorine, bromine, or iodine. And this attacks that and forms an ether, plus a salt. But I'm only asking for the organic compound, product or products. This is my R group. This is my R prime. The carbon with the halogen is that one. This R group comes along for the ride. Oxygen. What's my R group? Isopropyl. And we formed an ether. And it's your turn. What would be the organic product or products that you would make from that reaction? And when you're done, you know how to signal me you're done. All right. Thank you, Andrew. Thank you, Christiana. And we'll wait for everybody to finish, because that's the polite thing to do. Have you noticed Dr. White tries to always be polite? Why not? I should. All right. Let me get to work. How do we determine what's the product or products? Look for what's different, what's not carbon, what's not hydrogen. Ooh, oxygen minus sodium cation. That's what the plus means. This is an alkoxide. Actually, sodium alkoxide. Plus carbon, carbon, look for what's, ooh, a halogen on a carbon. Alkyl halide. Williamson ether synthesis. Remember, X can be chlorine, bromine, or iodine. And with that, this attacks that and forms an ether. And you get a salt, sodium halide, but you don't have to, this is an inorganic. So, I'm not going to worry about that. I'm going to call that R. That's R prime. Notice the carbon with the halogen will be the carbon bond to oxygen here. So what's R? Do you break carbon-carbon single bonds? No. You have an oxygen. What's R prime? Notice the N carbon of 3 carbons is bonded to the chlorine, which will now be bonded to the oxygen. And you've just made ethyl and propyl ether. Ooh, this is fun. Let's try something even better. All right, what two things would you react together to make those two things? Your turn. Like I said, this is the fun part. We call this synthesis. How do you make that? Thank you, Christiana. Thank you, Ignacio. And thank you, Andrew. It's time to get to work. How do you do this? You look for what's different, what's not carbon, what's not hydrogen. Ooh, oxygen with carbons here and carbons here. This is an ether. And ooh, we got something here, sodium chloride. That's a salt. Remember, X can be chlorine, which it is in this example, bromine or iodine. And how do we make an ether? The Williamson ether synthesis. And you have an alkoxide and an alkyl halide. So I can call this R. And this I'll call R prime. And if that's the case, then this would be my first thing, or you could make it your second thing, or it doesn't matter, plus R prime ethyl. What's the X? Chlorine atom, and that would be that. But wait, I'm not done. what if I call this R prime, and I'll call this R? And you can. Well, in that case, R is ethyl, so my alkoxide would be that. And then R prime is methyl. And this would be my alkyl chloride. Now, which one of these is correct? And the answer is they both are. And this happens many times in organic chemistry when there's more than one possibility of what to start with. Now, because your instructor, me, has many decades experience in the chemical industry, I know what's called cost accounting. And I know the raw materials here are less expensive than down here. Therefore, I would go with the blue one only because that would maximize your profits. In fact, do I have time? Yeah, I got a quick thing. When I got into management in the chemical industry, even when I became a bench chemist, but when I became a senior manager, I was in a meeting with marketing and salespeople and vice presidents and president of company. And someone said, well, this is better for our gross margin. What the heck is that? Well, I asked someone, they told me, and my boss came over and said, did you ever take accounting? No, I'm a chemist. Said, well, go get an accounting book and learn it. And I did. I called my accountant, what's a good accounting 101 book? And one of the, how should I say, at that time, things I realized I should have done either in undergrad or grad school was taking accounting 101. Because I had to learn real quick what was EBITDA and other things like that. That's earnings before taxes, or what's indirect or direct costs. But for this class, good news, you don't have to know accounting. So this is an ether. Let's move on. Now, I'm not going to go through any reactions of ethers because ethers are pretty unreactive and they're used for many times, which I've used often in organic chemistry, as a solvent. That's a liquid you run the reaction in. There's a branch, but most reactions in organic chemistry are in a solvent. They're not mixing two solids together and let them react. In fact, in graduate school, I used this ether. It's a cyclic ether. This is called THF, which is short for tetrahydrofuran. It's a common name for that ether. And I used a lot of that. In fact, I and others in my research group that I was part of, we used this where it was ultra, ultra pure to the point we distilled it from sodium. We had a still set up. Went through a lot of that. All right, let's move on. Wrong thing. Right thing. Nope, wrong thing again. Hold on. Let me just do that. All right, I see where I confused myself. And guess what time it is? It's new functional group time. And this is called an epoxide. Now, I have it written here. An epoxide at first glance you think is an ether, but it's not. It's a separate functional group. An epoxide in the simplest form are two carbons that are both bonded to an oxygen. So you have a three-member ring, two carbons, oxygen. Now, these hydrogens can be replaced with carbons, so you can have R groups on them. They can be the same or different. For this class, I'm going to stick to simple ether, and that's this one right here. Now, this molecule, which I don't ask you to learn the name, I'm not even going to names of ethers, is called ethylene oxide. And ethylene oxide is widely used in industrial organic chemistry throughout the United States and the world too. And I worked for 2 different companies that use ethylene oxide. Now, Dr. White's going to try and be a good chemist and not use slang. If you work with ethylene oxide, which I have for many years, we call it EO. But since you haven't, I'm going to try and be a good chemist and call it ethylene oxide, not use slang. Now, ethylene oxide is an extremely dangerous chemical. Why? If you get enough oxygen in ethylene oxide, it will blow up, which makes it, and we're talking oxygen like from the air. In fact, one company I worked at, and this was, then it was PPG Maser. It's now got a different name. It was sold off by PPG. And that was located about 3 or 4 miles northeast of Great America in Gurnee. And one afternoon, we were sitting around on a Friday before we were all going to leave. Friday afternoons, a half hour before, we'd sit around the research group and shoot the breeze, talking about things. And someone asked, if our ethylene oxide tanks blew up, would we take out Great America? And we all knew if they blew up, we'd be dead instantly. Because our research center was within a half a block of the plant, and they had 2 500,000-pound tanks of ethylene oxide. If they blew, you'd be dead before you knew it, I think. Luckily, they never blew up. But the consensus was we'd cause some injuries and knock down some stuff possibly in Great America, but it wouldn't be widespread death. It would just be close by. Now, do I have time? I do. Are you ready for a freaky Dr. White story? This is really spooky. I should wait till Halloween, but I don't. Well, I was hired by PPG Maser. One of the things was to improve their quality control, which I'm an expert in, to make sure your products going out are high quality. And one of the things I was asked to do was to improve this test to measure certain things for the key product they made. And the chemist who came up with or developed the test for PPG was in their headquarters in Pittsburgh. So after a while playing with it and trying to improve it, I went to my boss and said, who's the chemist who originally came up with this? I need to talk to him. And he said, that's Dr. Dahmer. And I said, without thinking, and I do this a lot in my life, I said, that isn't Jeffrey's father, is it? My boss said, yes. And please don't ask him about his son. And every time I talked to him, back of my head, there was a voice saying, ask him what happened with your son. Ask him. Luckily, I never did, but that voice was always back there. Ask him. And I never met him face to face. We just talked on the phone a lot. And this was before, unfortunately, or fortunately, however you want to say it, unfortunately, really, his son was murdered in prison. You don't know who Jeffrey Dahmer was. He killed, I don't know how many people in Milwaukee, I think it was, and cut them up and kept them in his freezer. And I don't know if he ate them or not. Yeah, I ruined your day. I ruined my day. But it was bizarre, to say the least. Chemistry has provided me with a lot of interesting experiences. That's got to be one of the more bizarre ones. All right, let's talk about ethylene oxide. Now, switches off for this reaction, everybody. You don't want to ever get water with ethylene oxide. One, it can form explosive stuff, and two, it also reacts to open it up. This 3-membered ring is constrained, and it doesn't want to be a 3-membered ring. So oxygen, carbon bonds, you can break like that, and this does. And water, H goes to the oxygen here, OH goes to carbon, and you make ethylene glycol. You don't want that to happen. Again, switch was off for this reaction right here. Now, switch is on. And I have it written this way, and I'll rewrite it on the whiteboard. Let's talk about reacting an alcohol with ethylene oxide. All right, thumbs up, people. Do you see my whiteboard? Thank you. So if you take ethylene oxide and react it with alcohol, remember, these bonds break real easy. It doesn't want to be in that three-membered ring. It's constrained. So it does. And what happens? Is you make this ether alcohol. There's an ether there. And this is an alcohol. And it turns out these type of molecules are very useful in products you buy already. And I'll talk about that. So let's take a look at this reaction. Now, this reaction and next one, I will never give a synthesis problem on a test or the final, because that's cruel and unusual punishment, and I don't do that. But you should know what's the organic product or products are the following. How do you do this? And you look at this, what's different? Ooh, carbon-carbon hydroxyl group, alcohol. This is ethylene oxide. Now, there's also propylene oxide that I've worked with. By the way, I forgot to mention, at one company, when I started working with ethylene oxide, I was warned if you mess up, you're dead. This separates people who should be organic chemists from who won't, because it's scary the first time. Afterward, you learn how to be safe. And what you form is this ether alcohol. And this product, what's our ethyl? So therefore, I have my ethyl group, I have my oxygen, then I have my CH2, CH2OH. And that's what happens. Okay, well, let's have you have some fun. And here's something for you to try. What would be the organic product or product for the following reaction? Thank you, Christiana. And I'll wait for everybody else to finish. Thank you, Andrew. Thank you, Ignacio. Now I can get to work. All right, we look at this molecule. What's different? What's not carbon? What's not, an oxygen with a hydrogen and a carbon? Alcohol. And what is this? Ethylene oxide. Excuse me. And what do you get? This ether alcohol. And what's my R group? 4 carbons. So I'm going to have 4 carbons because you know you don't break carbon-carbon single bonds. No, you don't. So here's my R group. The carbon with the hydroxyl group will be the carbon to this oxygen, the end one, and then CH2, CH2, OH. I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And we're done with that reaction. If I look at the clock, it's time for about 30 seconds of break. So I'm going to give you an extra 30-second break. Come back at 2:50 and we will continue this, and we'll also do the lab for today. I'll see you in 5. I'm back. All right. Now, one of the things I'll be doing more and more, and I've said, is talk about why are you learning this stuff, besides the obvious reason you want to get a good grade in my class to get into school or program. And let's look at the reaction you just did. We take 1-butanol or N-butyl alcohol, react with ethylene oxide, we make this molecule. Now, I'm not going to ask you to learn how to do the IUPAC, but this is called 1-butoxyethanol. And so what? Well, guess what? My parents raised me to be a socially responsible person, and I am. And I'm a socially responsible person with a lot of knowledge of organic chemistry. And let's talk about something that I think you should know about. Back in 2010, can everybody see the Wikipedia Deepwater Horizon? Thank you. There was a what would be the right term? An awful environmental tragedy that happened in the Gulf of Mexico. And BP had a oil well, that a valve broke and they couldn't repair it. And for many days, lots of oil, crude oil, was released to the Gulf of Mexico. And I followed this because I'm an organic chemist. I was wondering what it is. And I found out by my calculation what BP and the government were saying, how much oil was being released per day in total was way off from what normally an oil well would release. Because I looked up those numbers. Now, because of that, oil, and oil is lower density than water, it was floating on the top of the water. And it was a tremendous environmental tragedy happening. Well, BP and they hired some people, and the oil well drilling company used a dispersant to try and disperse the oil throughout the ocean. And what they put in was a dispersant from a company called Nalco, which is located in Naperville. And I looked up it was called, I can't see the name right now, but I can't, I'm getting a mental block. But anyways, I looked up that chemical and I've got a mental block. Let's go back here. Or exit. I couldn't think of that name. But anyways, here's something to learn about why I'm teaching you. This will never be on a test, but you can use this the rest of your life. Every chemical that's made in the United States, that's used in the United States, there's called what's called the material safety data sheet. And I looked up Corexit, and I think some of them have been taken down since this tragedy. Go to Google, put in the name of a chemical, put in MSDS, Material Safety Data Sheet. And notice you'll see some. And here's one, I think it's been sanitized since that. But let's look at one. And this is when it was still owned by Nalco. And MSDS sheets are the same. I've written some for molecules I invented in companies with the help of our certain other officers. And it always has composition. And notice the first thing, 30 to 60%, is 2-butoxyethanol. And at that time, oh, I wonder what that is. Because the other stuff I knew what they were. They aren't dangerous. So what did I do? Go to Google. First of all, copy it. And then put in the name of the chemical, MSDS, and you can find these. And Fisher is a well-known or chemical company, or actually distributor, and they have different names. And here's 2-butoxyethanol and hazards. And this is a newer one. The older ones were better. And it's like I said, this is newer since 2012, but flammable 4, toxicity 4, 4 is the highest, inhalation 4. If you read the old ones, they say that it will kill marine life and it is very toxic and hazardous to the organs in human body. Well, when I read that, and they're dumping millions of gallons of this into the Gulf of Mexico. So what did I do? I called in charge of that, the Coast Guard, who was in charge of that cleanup. I was able to get to the second command, said, this is dangerous stuff. He said, no, our chemist has told us it's not. Oh, let me talk to your chemist. Well, he gave me the number, and turns out there was an academic chemist. Not that there's anything wrong with academic chemists, but they don't have the experience industrial chemists have. And he wasn't even an organic chemist. He was an analytical chemist. Not that there's anything wrong with analytical chemists. So I talked to him and he said, oh, it's not that bad. I said, did you read the MSDS sheets? So I don't think it's that bad. But I realized I was up against the wall and they were still dumping millions of pounds of this into the Gulf of Mexico. So what did a socially responsible organic chemist do? I called the New York Times, I called MSNBC, and I also called CNN. And I let them know about this, and I explained about the MSDS for the main component. Well, hopefully I wasn't the only one who did this. Well, within 24 hours after I called, hopefully others, those stations started in the newspaper saying, this is bad. And they got on the EPA, and it took the EPA another day or two to finally stop BP from dumping that in there. Follow up, many years later, I saw this article about someone who had been cleaning up and was a newspaper person and had volunteered to help clean up the oil spill, like cleaning up birds or going out in a boat, trying to capture the oil spill and get it off the water. And he didn't write this article. Someone else who knew him wrote him about his experiences then. Well, I emailed that person, got to talk to him, and I said, I had done this, what I just told you about, calling the Coast Guard and everything else. Well, this person said, well, let me have this person call you. And I talked to this gentleman. This is a number of years ago. This is like 10 years after 2020, a couple of years ago. And we're talking, and he was telling me I followed up with other people who were on the boat with me or cleaning up. And what you just described, because I told him some of the things I'd read in the MSDS sheet said, we're now suffering those. And it was just so wrong that it went on like that when someone should have looked at the material safety data sheet. Now, not all uses of chemicals are bad. That same chemical, 2-butoxyethanol, can be used safely with proper ventilation in oven cleaner. It's a good one. And if you buy the easy off cold, not the hot oven cleaner, its main component, if you look at the label, is 2-butoxyethanol. So why do we use why are you learning the reactions I'm teaching you? Because they're used to use products. Now, sometimes if those chemicals are used in the wrong way or an unsafe way, bad things happen. And it also hurt this fishing industry in the Gulf of Mexico for many, many years, that using that chemical, and the oil spill too killed off a lot. And remember, I'll never give you a synthesis problem here. All right. I'm going to do something right now. Do not copy it down unless you want to, but you don't have to. And we'll go for a while, and then we'll do our lab. So if I do this reaction, what do I have? An alcohol plus ethylene oxide, and I get an ether alcohol. And what's our methyl? So I'll get this molecule. Now, if we look at the new molecule we just made, what do we have? An alcohol. And guess what? I can react it with more ethylene oxide, and I'll put it here. Now, this will not react with this ether, so my new R group is this, but I'll still use the same reaction. And what I'll get, here's my R group of the new alcohol, and then oxygen, CH2, CH2, OH. And this is a new one. Now, if we look at this molecule, what do we have right here? An alcohol again. And guess what? I can react that with more ethylene oxide. And my new R group for this reaction is that. So I'll rewrite that. This is my new R group. And then I'll have OCH2, CH2, OH. Now, if we look at this new molecule, I have an alcohol again. I can react it with more ethylene oxide. And I can be like the Energizer bunny, boom, boom, boom. You know what I'm talking about. And keep on going and going with this. Now, let's look at something interesting. This molecule right here, what are the repeating units? 1, OH, OCH2, OCH2. And there's 1, 2, 3 of them. And as I said early on, I don't use this as often. Repeating units you can show in parentheses. Another way of writing this molecule would be this. How many repeating units? 3. Then we have this hydroxyl group on the outside. And that's how you do it. Ooh, 3. I added 1 mole of ethylene oxide, 2 moles or molecules, 3. Ooh, that's interesting. And why? Because this is the next reaction. Why did 0? That happens sometimes. And this new reaction, which I have on the slide, and I'll rewrite on my whiteboard, switches on. Uh-oh. Hang in there. I got to close things. This is when I get to the exciting part. All right, we're back in business. Now, you can react, and I'll rewrite this, a alcohol with more than one molecular mole. Remember, a mole is the counting unit of chemists. And if we look at the reaction I just did, when we used 3 moles of ethylene oxide, N was 3. So let's look at this general reaction. And this one I'll never give a synthesis problem on. If you take an alcohol and react it with N moles of ethylene oxide, you'll have this molecule, where now I won't write them out. That's a C. You'll get this polyether alcohol, where this end, how many moles, is
We
how.
can't see. We can't see.
Oh no, I do that. It's rare, but I have. Thank you for letting me know. All right, let's do this again. Can you see it now? Thank you. If you take this alcohol, react it with N moles of ethylene oxide or molecules, you get this polyether alcohol, R bracket OCH2, CH2, close bracket N, OH. The N comes from the number of moles. Now, when this was 1, it was this R, OCH, OCH, OH. And here, where it was 3, you get this. And this turns out to be an important reaction. The story I told you with Dr. Dahmer, the reaction where I was trying to improve the analysis was of these type of products. And in organic chemical industry, N can be anywhere up to 100. It could be more, but realistically, usually it's 1, 2, 5, 10, 15, 20, up to about usually 50 is realistic. You can have special order more. So let's take a look at this. And here, if we take this reaction, what do we have? Alcohol. What do we, ooh, that's unusual, a number, N, and ethylene oxide. And what do you get? You get this polyether. We show that by this bracket, OCH2, CH2, close bracket, N, which is this number right there, and then outside the bracket, OH. Common mistake students make, and this is test 2 material, is they put the OH inside the bracket, and that's wrong. So what's our, actually I should have this. So since I don't break carbon-carbon single bonds, then I have O, CH2, CH2, close bracket. What's N? The number here, 5. Then outside, I have this bracket. And that's how you do it. And here's one for you to do. And again, I'll never give a synthesis problem for this reaction or the previous one. When you're done, give me a thumbs up. Thank you, Andrew. Thank you, Christiana. Ignacio, did you step on your cable? Or are you just having bad internet problems?
Yeah, it's going in and out today.
Sorry to hear that. Do you live in an area now where they have Astound, which used to be Wow? Switch them. I use them and they're really good. Anyway,
Really? Okay. Yeah, we have Xfinity, and
I've
it's
heard
been
that.
problems for the last year.
If you have Wow, what used to be Wow, now is about Astound, switch to them. They're good. I used to have Wow, and now they got bought out by the other company. All right, let's do this. What do we have here that's different? An alcohol. What's the R group? A ring. Ooh, that's unusual. I have a number there, N of ethylene oxide, N moles of ethylene oxide. And what do we get? This polyether alcohol, where N comes from there. Well, what's our R group? This ring. Then it goes to an oxygen, CH2, CH2, close bracket, what's N? 4, then OH. And that's what you get. Oh, let's do one more. Let's have some real fun. And there's something for you to have fun with. Looks like we lost Ignacio again. Well, you can watch the video. Now, let me help you out. The C9H19 is a CH2, CH2, and CH3, 9 of them. A benzene ring will not react with ethylene oxide. Carbon with a hydroxyl group, ooh, an alcohol. Now you can proceed. We talked about you behind your back. No, we didn't. Well, anything you missed, you can watch on the video. I just told the class that the C9H19 is a CH2, CH2, a CH2, and a CH3. That won't react with ethylene oxide. And this benzene ring will not react with ethylene oxide, but this alcohol will. And don't forget, tonight I have my office hour, and you should have received by now, and you have until tomorrow, 4 p.m., to do test number 1 and upload it. If you have any questions later today, tomorrow morning, and tomorrow, let's see, tomorrow's Thursday. Tomorrow morning at 9, I have a dentist appointment, but after that, I'll be home. So if you need to contact me because you have questions on test number 1, feel free to email me or come to my office hour tonight. And when you're done, give me a thumbs up. Thank you, Andrew. Thank you, Christian. Thank you, everyone, Ignacio. All right, let's take a look at this. This is my R group. Oh, I've got an alcohol. Ooh, a number in front of a molecule. I'll call that N. And the molecule it's in front of is ethylene oxide. Notice I've been good. I haven't used slang. And what do you get? this polyether alcohol. Well, this is R, so I'll rewrite it. And then I'll have my bracket. Oh, that two O's, no, only one. O, CH2, CH2, close bracket, what's N, 9, and outside OH. Now, that's how you do this. And as I've asked a couple times today, why are we learning this stuff? Well, the obvious answer is you want to get a good grade to get into school or a program like nursing school. A number of students in the past and probably now are planning that, or a nutrition program, or others, or a physician's assistant. But let's take a look at this. And let me go back to my slides. And here's the reaction I just covered right here. Now, I'm going to talk about things now and the rest of the semester I'm in no way taking a moral stance on. It's just organic chemistry. The molecule you just made is this one, and it's got a trade name, nonoxyl 9. Benzene ring, nonyl group, that's what C9 alkyl group is, and it's got 9 moles of ethylene oxide reacting to to give this. And what is this used for? It's a surfactant. And where's the main use? A spermicide. Yep, a spermicide. What's that? And here, let me move. Can you see on the right the structure? The R group, 8 CH2s and a CH3. And here, benzene ring, O, CH2, CH2 in a bracket for 9 OH. This is called nonoxyl 9. And it's a spermicide. Where do you find it? If you go to your local big box store or other places, again, I'm not talking moral stances, it's life. And you look for condoms or prophylactics and the lubricated ones in the lubrication on the outside. If you look, pick up the box, and if you can go to Walmart, and you can, you'll see it contains nonoxyl 9. Now, how does it kill sperm? Don't know. I think I read somewhere it stops them from being mobile, but I don't know. And this is also found in vaginal contraceptives, foams, where it's also, and it's the thing. And I think the word I was using is for cervical variable. Now, interesting enough, it's a lubricant and it's used in shaving cream. And I guess that's explaining why my face never got pregnant or yours didn't either. And it's also used as a surfactant in cream to remove the itch from poison ivy. Surfactants work at the interface of surfaces, the chemical in your skin, to help draw it out. So there are different uses, but how do you make that? You take nonylphenol and react it with 9 moles of ethylene oxide. So why are you learning this stuff? Because it's stuff to make things people buy and help people in their daily life. And this, like I said, for poison ivy cream or for spermicide in condoms. I look at the clock, I better do the lab. So it's lab time. Let me close this. Let me go open the lab. Let me make sure you can see it. All right, better check. Everybody see our aromatic electrophilic substitution lab? Now, if we were doing this in the lab, I'd be at highest level of observation and keeping an eye on every student at the same time, because we'll be working, if we were, with sulfuric and nitric acid. These are very hazardous chemicals. Now, today's lab deals with reacting electrophile with a benzene ring. And you learned about that when we did aromatic electrophilic substitution. Now, remember, what I do in the lab will never be on a test. Now, what happens when there's something on the ring, Z? Well, Z affects the electrophile coming in by stabilizing or destabilizing, depending what it is. Now, you could have the electrophile going in the ortho position. It could go in the meta position, or it could go in the para position. And this lab, you're going to find out if the following reaction is bromine director. What type? Now, it turns out, and let me go to my whiteboard and pay attention. There's only two types of directors. One is orthopara, the other is meta. Now, once in a while, if Z is real big in an orthopara director, you will not see any ortho, but it's still called, if you just get para, it's still called orthopara director. I'll say that again. Sometimes when Z is real big, it blocks the ortho position, so you'll only get para, and it's still called an orthopara director. If it goes to the meta, it's a meta director. In this lab, you're going to find out, is bromine an orthopara, or is it a meta director? Now, the overall reaction is starting with bromobenzene and reacting it with a solution of nitric and sulfuric acid. Now, since I'm not going to give away the answer, I'm going to just write like this. That somewhere on the ring, there's going to be a nitro group. This is not the answer, because I don't want to give away where the nitro group will be. It's going to be ortho, it's going to be ortho and para, is it going to be meta? And you'll see why I'm writing this in a second. Now, why do we react the nitric and sulfuric acid together? And this, pay attention. In the procedure, you take, when it's very cold in an ice bath, you take the sulfuric acid, which I'll say is H+, and you add nitric acid, which I'll write like this. Pay attention. And what happens is it protonates this right here, meaning it becomes H+, adds there, and you get this intermediate. I write the brackets because you can't isolate it. This immediately loses water, C2 hydrogens oxygen, and it forms this nitronium ion. And this is the key reactant, because this has a plus charge and says, I don't like that. Where's some electrons? And the pi bonds on the benzene ring have a lot of electrons, and it attacks that. So remember that. Now, here's some YouTube videos you can watch, but if we were in a lab, we'd heat some water, because eventually you'll boil it. We put boiling chips in, I'll talk more about in another lab, so it doesn't bump up and splash up when it's boiling, because that happens when you do that in glass. And I'll tell students, don't touch a hot plate because it's hot and you'll burn yourself. And I've had one student who didn't listen to me. Guess what? He burned himself. You don't put your hand on something that's hot. And in a round bottom flask, you'd add the concentrated sulfuric acid with a funnel, and then you would add slowly, well, you cool it first in an ice bath, then slowly 3 milliliters of nitric acid in 3 parts dropwise, because it gives off a lot of heat, exothermic. Then after 2 minutes with swirling, you'll add in the round bottom all the bromobenzene, and you'll let it sit for 1 minute. Now you'll take it after that out of the ice bath and watch the videos and let it come to room temperature, because you're going to put this next into boiling water to react it longer. Now, when you put it, and we're doing this all in a hood, which takes any vapors out of the hood and shoots them to the roof of the building, and the air dilutes it so it's safe. And time for a water break. This is thirsty work. Because of a side reaction and I'll have to get it back. But anyways, because of a side, 3 more rings, I think. 2 more. Hopefully the last one. I was wrong, I miscounted. Last one, stop. Thank you. All right. Because of a side reaction, when you do this, out of the round bottom top, you'll see this brown smoke. And if I hadn't warned you, you'd be scared. What is that? Well, it's nitrogen dioxide, and it's a poison, but you're in a hood, so you don't have to worry. Now, since we don't have enough time to isolate this, I asked students in this lab to take it out of the boiling water, let it cool, and you should see a solid. That's the bromonitrobenzene. Now, if we had another hour lab, which face-to-face we don't, I would tell you, first of all, I tell you where to put the waste and how to take care of that. I would have you, first of all, I would initial it. This is my initials, a K inside a W. And then if you were in a lab and we had more time, which even face-to-face we don't, but I tell you, because I've taught this at other schools, the melting point of your product is 121 to 123. Now, right here, you have to identify what you make. How do you do that? You look at this chart. Now, when you do melting points in real life, it's always going to be a little lower than the actual product. So from this melting point, you can figure out which is the isomer of bromonitrobenzene, and you identify it right here. Next, here's some questions. Notice, draw the structure of the key reaction product when you mix sulfuric acid and nitric acid together. Next, draw the main product. In other words, what you wrote here. And then what type of director? You got 2 choices, orthopara or meta. And then here's another question I'll let you read on your own. And with that, I'm done for today. We're done for the week, unless you're coming to my office hour. And I guess we lost Andrew, or not Andrew, I'm sorry, Andrew, lost Ignacio. Bad internet connection, sorry to hear that, but he can come back and watch the video. But remember, you should have gotten the password for test number 1. Take it, upload it when you're done, either as a PDF file, either scan it or use a cell phone. I was going to say a smartphone, Anybody ever see a dumb phone? Anyways, use your cell phone, and I have instructions how to make that into a PDF file 2 different ways. And then make sure by 4 p.m. you upload it to D2L. And with that, I'm done for today. And I'll say, gang gesund. If you come to my office hour later today, I'll see you. If not, have a great rest of the weekend, and I'll see you on Monday. Gang gesund. Bye.